Hello, my name is Brian, and I am a part of Team Juno with Danush, Tristan, and Wenjay, with our advisor, Professor Mohammed El-Hadedy. We are going to present our reconfigurable S-curve motion controller project for the Artemis mission.
The disadvantages of the industrial motion controllers that are used today is that they are specific to kinematic and tool types. Also, the software is not open to the public to use for their own projects. Additionally, it is very expensive, made for industrial use only, and it is difficult to use. As of today, the more known open source motion controllers are Atmel-based GRBL, ARM-based TinyG. However, we cannot expand on their work and fit it to our own personal needs. They also lack proper safety measures, and they are very limited in how much movement they have. Our goal to assist the Artemis mission by developing a reconfigurable S-curve motion profile platform to enable various devices to safely and reliably deliver sensitive payloads on a mission. Whether it is a rover on the moon or a drone from Mars, our reconfigurable controller will be able to be applied onto any motor control device. By processing the SLAM camera data using computer vision analysis and using the output of the analysis as feedback to the proposed reconfigurable motion controller profile, the system carrying the controller will manage to serve in rough terrain environments. As you can see in the picture, there are two different motion profiles, the trapezoidal profile and the S-curve profile. The trapezoidal profile is the original motion profile. However, at each point on the trapezoid, as highlighted, is a change in acceleration and deceleration. Due to the change in motion, it causes jerk. To eliminate this, we have implemented a S-curve profile, which mathematically is a polynomial of 2 degrees or higher order profiles. Our velocity, S-curve, can be mapped to a motor frequency.
For our project, we aim to construct a forward-feeding motion profiling system. Characterized by its robust construction and reconfigurability, it can be applied to a variety of commercial to industrial applications. With our custom user interface with end-to-end control of motion profiles, we will demonstrate in a closed-loop application such as our radio-controlled vehicle and drone platform. So the traditional approach to generating motion profiles is to derive the formulas of all the piecewise functions when the simulated or highest order of the motion profile is determined. As you can see in the bottom right plot, the jerk profile, which is the third order derivative of displacement, is our highest order amount of all these profiles. It is simulated with a square wave, which can be written as a piecewise function. From there, we can generate the closed form expression for the corresponding acceleration, velocity, and displacement. This approach is advantageous for a specific closed source application because the mathematical derivation can be done only once before runtime. So we only need to evaluate the formulas to generate the profiles at runtime. However, it is not reconfigurable because the order is predetermined and fixed. One of the uniqueness of our free-forward profiling system, as you can see in the high-level block diagram, is that the number of integrators used is determined by the user input, order n. Notice how our system has constraint on the range of n based on different trade-offs. We allow users to set the most generic but essential parameters in the motion profile, namely total distance with total time and total distance with maximum velocity. These two options cover the need in most applications, and we also provide the simulation mechanism for signal X, namely, we allow users to pick the waveforms but don't require them to set all boundary conditions of the piecewise. After integration, we scale the displacement curves based on the user given constraints. So our first idea is to extend the traditional approach. Namely, our implementation derives all closed form expressions for all piecewise formulas. Specifically, we derive all the piecewise formulas based on the user given order that varies in real time. To achieve reconfigurability, real-time computation now includes both derivation and evaluation of the piecewise function. Even though some parts of the derivation can be pre-computed based on our implementation, the plot shown on the right shows the order we evaluate the intervals of all the piecewise functions, namely in the vertical order, first the same interval of all the piecewise, then move on to the next interval of the piecewise. However, this approach is very susceptible to runtime and memory issues. We will look at an example to illustrate these issues. As order m increases, we will have 2 to the power m minus 1 intervals for m levels of piecewise. Each interval has a closed form expression of some polynomial consisting of potential maximum of m terms, which is a large number of formulas to derive, store, and evaluate. To optimize this approach, we develop an efficient data structure for storage, namely only storing the coefficients of all the terms in each polynomial in order of increasing value. We also store the basic pattern of integration as shown here for the convenience of our integral derivation, as we can simplify access to the right element inside the array. Multiply each term with the coefficient from the previous level of the piecewise and add the offset evaluated from the previous interval.
To control the system delay on an edge device such as a Raspberry Pi, we came up with a discrete implementation of the system. We simulate the highest order profile as sampled points in an array and use digital integrators implemented in Python. Notice that even though the error in approximation can accumulate over time with digital integrators, by using symmetry to generate the profiles, we can minimize this error and also optimize runtime and memory usage. Another advantage compared to analog systems is that we don't have to store load and evaluate formulas for all intervals of a piecewise function. On the right, there are two plots of the velocity S-curves, with different orders generated by the digital system, one with a specific total time, and the other with a specific maximum velocity set by the user. In each case, we can visualize the improvement of the smoothness at the corners of the profile as order increases. Here's an example of how we made use of symmetry. We only stored 3 intervals of the highest order profile, sampled them into an array, integrated it, and padded it with the negative version of the array after padding it with the right number of zeros. And then we repeat the process. In this way, we don't have to integrate over potentially a large number of points for all orders, which not only saves runtime, but also decreases the accumulation of error integrating in discrete analysis. To better visualize our data analysis, we generated the following 4D plots. Using these, we calculated our Vmax, or max velocity. On the right, you can see how by changing time, distance, and order, we calculated our Vmax. As the orders got higher, so too did our Vmax calculation. Conversely, on the left side, we changed our distance, order, and set a max velocity threshold. From this, we calculated our time. This form of fixed time analysis also yielded comparable results. As the max velocity threshold was set lower and our distance was set higher, so too did the max time calculations that we calculated. We use the same approach in our generation of the A max values, or acceleration max. On the right, you can see how by changing distance, time, and order, we're able to calculate different A maxes. However, in our fixed time analysis, we can see how by changing distance and max velocity with a fixed time, we're able to generate a similar A max. However, the trend is different as well. For example, one limitation in the right plot is that due to the way that fixed time is handled, it instead is deprecated through and half of the values are lost in the generation of the 4D plot. This is most likely because in our calculation with recurrent derivatives, many of our values, such as positive exponents or any powers, overlap and thus are double represented and lost in our 4D plot. This is solved in our left plot, where we can see a thorough representation of all values and generate a better overall trend for analysis. From this, we can see how in lower orders, we see more acceleration max and less continuity and linear trends. Lastly, we also generate 4D plots to better visualize our calculation of Jmax, or max jerk. On the right, we can see how by changing distance, time, and order, we generate different J-maxes. This is similar to our left approach as well. However, in our fixed time analysis on the left, we change distance, order, and set our max velocity. From both trends, we can see how by generating the different Jmax values, we see many of our values aggregated towards certain corners per se. For example, on the right one, as we decrease our distance and our time, we see the majority of our data aggregated towards this corner as our values drop significantly. This is similarly seen in our fixed time analysis on the left, where most of our Jmax is aggregated as our distance gets lower, but our max velocity threshold is set higher.
Our project work aims to expand upon a predecessor group that used the Pink Z2 board to implement the first order S-curve and trapezoidal equations in Verilog. Our design is now different from theirs because we have decided to use the software generation of the profiles from a Raspberry Pi, as it is simpler to meet deadline-wise and to support our method 2 reasonings of implementation as stated previously. Here's a video of the previous group's implementation of the S-curve motion profile. We've assembled our own 3D printer-like grid to test all our experiments on. This is to show that as we go on in the project, we want to have first to third dimensional movements on the same platform to test and verify that changing our hardware setup doesn't affect our results. We have a system of pulleys that has one motor moving one axis each. And for now, our aim is to start from the first dimension and work our way up, continually improving the structure, as well as changing our code or setup as a need-to-need basis, depending on our results. We'll start out with the simplest implementation of straightforward and back motions. Our main targets will be stepper and DC motors driving a payload with our algorithm. Each motor has their own specific properties that apply them to various different applications, but our goal is to show that our algorithm will work regardless of that platform. This is the first step to proving that our system is truly reconfigurable and will be adopted and accepted as a trademark one-for-all system to use on any kind of motor driver device. For our first case, we've decided to go with an open loop stepper motor implementation to replicate CNC machinery. The idea is that with a well-optimized microstep value for accuracy and performance balance, we can control the rate of steps to match the generated plot based on our bore's pulley size. The Raspberry Pi will generate our profile and control the motor by sending the appropriate target frequency after velocity conversion to the driver discretely based on the input settings. Here are the results from our open loop implementation with inputs of distance equals 6 centimeters, total time is 10 seconds, and order equals 4. The data presented in the figure is from an HC SR04 ultrasonic distance sensor reading from a secured point on the grid. This represents two function calls for forwards and backwards of 6 centimeter and 12-second traversal with 1 second of delay in between. Our readings are imperfect and fuzzy because of the sensor, even at idle, seems to have bouncing between the distance reading. However, we believe that because this is an open loop iteration of the process, that it's valid to believe that with an improved system, such as closed loop encoder feedback, we'll have more accurate data readings and less sensor noise. Based on the findings of the first experiment, we've decided to transition to a closed-loop PID DC motor system to replicate a drone's propeller motor movement. Our feedback system will be a velocity-based encoder system that is driven by an Arduino that receives serial connection of target values from the Raspberry Pi. Thus, using that target value as the input for the PID, and our feedback will adjust the duty cycle based accordingly from the current sampling rate of the encoder count from the interrupt pin. In our initial data readings after tuning the PID system with the Ziegler-Nichols tuning method, we discovered that we had an issue with dealing with startup current of our motor, losing resolution at the start of our profile. This issue is addressed by starting the motion using an offset RPM and not starting at a zero value. For our case, this is an acceptable solution because drones will often prime their motors before takeoff, resembling our running start solution. We can analyze the distance translation after removing the offset and verifying the resulting change in distance based on the time that we had used that offset. Here's a demonstration of our free run movement. The recorded data strongly resembles the generated profiles from the encoder readings. Therefore, the most practical application is with closed-loop feedback to ensure motor speed and accuracy. The input values for the graph were distance equals 100 centimeters and max velocity is 10 centimeters. A Matlab script was used to analyze that our implementation is accurate within a max error of negative 0.4 centimeters of any given point. We also verify that our previous inputs get us to the correct destination and that our algorithm has proven valid on two very different motor cases with given some driver function adjustments, and given that the offset value of our previous DC motor implementation.
To better visualize our DC motor analysis, we decided to then employ it on a radio-controlled test fixture. In practical applications, we start to see a rapid increase in remote deployments and search and rescue missions using UGVs, or unmanned ground vehicles. And this is why we decided to implement our open-loop DC motor analysis in such a fixture. We used a recycled RC chassis, reconditioned 18650 LiPo cells, ESP32 microcontroller, El-Hadedy motor controller, and MPU 6050 sensor. Here's our overview of our vehicle architecture. We start with our power source, the 18650 LiPo battery cell. We reclaimed these from an old battery pack and were able to recondition them for our purposes. These power our microcontroller, the ESP32. Using this, we're able to host our two web servers, one for data visualization and the other for user control. All DC motors in this case are controlled by our El-Hadedy motor driver. Using the two H bridges on board, we're able to control two DC motors if we choose so simultaneously using PWM inputs from our ESP32. We also made use of bypass capacitors in order to use any high frequency noise induced by the motor. The ESP32 microcontroller establishes our Wi-Fi connection and hosts two asynchronous web servers on localhost and ports 80 and 81. We use SPIF's library to generate our file system on the microcontroller, through which we transfer our HTML and CSS files. The user can trigger the open-loop S-curve simulation, while also dynamically visualizing the accelerometer data on the other web server. Below, we can see the UGV testing demonstration. As the user triggers our test, the accelerometer picks up the constant acceleration over different periods of time and maps it on our plot to the left.
Due to the nature of most commercial drones being closed source of their flight software, we built our drones from scratch using the Pixhawk 2.4.8 flight controller and an Evo 2, both supported by a companion computer Raspberry Pi to generate our code and drive the drones through the DroneKit API. The assembly process was quite time-consumptive as the COVID pandemic slowed down our timeline significantly. We are currently in the process of testing and calibrating sensors as well as the motors to ensure a stable flight. Our code compiles and sends the drone commands for point-to-point flight, but further improvements need to be made for stability in order to get it to fly. We followed many online resources to assist in assembling the drone. Most frames and bases needed to be soldered on, but the core components were the Pixhawk/Evo 2, GPS compass component, 4 motors and their corresponding electric speed controllers, a lithium-ion power battery and its power module, transmitter receiver modules for testing and debugging, and a buzzer and arming switch. We believe that currently there is a fault within our speed controllers as the propellers do not consistently meet their target speeds as they should with certain transmitter inputs.
Introduce yourself, please.
Hello, my name is Brian Banta, and I'm part of Team Juno, and we're testing our
drone calibration to see if our motors are working correctly and see if any fail for any roll, pitch, yaw movements on our setup.
Sure. And I'm Professor Muhammad, Muhammad Ali. I'm the mentor of the Geno team, and we are now starting the test. Go ahead, Brian. The calibration have been done in the audio pilot and the mission planner, and thank you, we appreciate it.
Thank you.
Hi, this is Professor Muhammad Ali, the mentor and the head of the team Geno for the NASA mines, and this is actually test number 1 for the drones using Navview 2 as a flight controller. We try to do our best on fixing the whole entire drone with a lot of technical issues, and even due to the COVID-19 and all these problems we faced and the technical problem, but still we build the drone. And the previous video even show how the PixHawk work, and we are in the process of loading the motion control we developed as a team on the drone using Navview and the PixHawk. So what I have here is on my Linux machine, I set up the Q ground control while using the wire communication IP. I define the Navview on the board on the networking with the Q ground control, and I just arm it and is ready to use a radio controller for doing the test. So test should start now. First of all, we're gonna push arm and completely fall on the arm while the GPS is determining that I'm sitting now in the office. Then the controller will start doing the work. Going up and down, changing the communication after we calibrated the drone, and everything worked perfectly as we expected. And thanks a lot, and talk later about the next step for the other parts of the process. Thank you.
Moving forward, we plan on steadily making improvements to the drone configuration to ensure accurate and stable flight path data readings from the flight software. This means more calibration of the system and removing any faulty parts such as motors or electric speed controllers once we narrow down the issue. We will test a closed-loop stepper motor iteration and compare both data variations and their pros and cons. We will, in the future, proceed with a two-dimensional setup that uses feedback coupling and adjusts the code for various two-dimensional movements such as circular, straight path, or zigzag movements. In short, our list of accomplishments is as follows. We created a reconfigurable motion profile generating system that accurately creates arrays for velocity and time for the discrete domain. Created different versions of the code to accommodate time-sensitive tasks as well as velocity-constrained tasks, depending on the application. We tested and verified the real-world application of our code with stepper motors and DC motors. Built and assembled a custom drone that contains our code and is near ready for its maiden motion profile flight after some more work on the calibration. Thank you for listening to our presentation, and we look forward to hearing any feedback or questions about our project.